Okay, we are recording. Hello, my name is Sergio Garcia. This is me doing problems from chapter 9 and chapter 10 for the second extra credit opportunity for the final exam. I'm just going to pick 3 questions from the chapter 9 problems and then 3 from chapter 10. I'm sorry, not 3, 7 from chapter 10. And we're just going to go through it. It's just me for tonight. I typically work in my group, but our schedules just didn't work out this time. So roughly I'll be doing this on my own. I hope that's acceptable. I worked really hard to try and understand this material. So I hope just me going through it will be okay. All right, so we're going to start off easy with the chapter 9 questions. We're going to do the first question, right? So a turbine blade rotates with an angular velocity, which is given as 2 radians per second minus 21 radians per second cubed t squared. What is the angular acceleration of the blade t 9.10 seconds? All right, so let me get my pen out. So first thing you notice, they already give you your angular velocity. And that's great because that essentially already gives you almost the entire answer. And it also gives you time, which is very important. So this almost does itself. In order to do this problem, you just need to understand that your angular velocity, which is denoted at alpha, is the derivative of your angular velocity in respects to time. So if you take the derivative of negative 2.1 t squared plus 2, you're going to get negative 2.1 times 2t. And the reason that works is because if you take the derivative of 2, that's just 0. If you take the derivative of 2.12 squared, the 2 comes down and the exponent of t becomes 1. You can simplify that as having as negative 4.1 t. So we'll do that. Negative 4.1 times t is what our angular velocity should be. And look at that, we know what t is. So if we do some substitution, or not some substitution, just insert 9.10 seconds into this angular velocity equation, we'll get negative 4.1 times 9. That looks like a 4. I'm sorry, that looks like a 9, but it's a 4. In fact, I'll go back and I'll fix it. So negative 4.1 times our time, which is 9.1, is going to be equal to negative 38.2, which is measured in radius per second squared. And if you look over here, our answer E matches along with that. So our answer is E. All right, I'm going to clear this just because if I scroll down, it'll follow me. So I'm going to clear those drawings and we're going to move down. You can pick any question. Let's see. We'll do question 4. Let's do question 4. All right. So this question reads, let me get my pen out. All right, so this question reads that a 4-kilogram wheel that is 34.5 centimeters in diameter, which means that its radius will be double that. Wait, no, I'm sorry, half of that. Rotates through an angle that is 13.8 radians as it slows down uniformly from 22 radians per second. From 22 radians per second to 13.5 radians per second. What is the magnitude of the angular acceleration of the wheel? Okay, so this gives us a few things. If I come right over here, it gives us our mass, which is going to be 4.5 kilograms. I'm going to skip writing units. You know what units are what. It's in kilograms here. Our radius is going to be 17.25. And we get that from subtracting between, I'm sorry, not from subtracting, getting the average between 22 and 13.5. So like I can do the math for you, but you have a calculator. I'll just check my work really quickly. I'm grabbing my calculator. So 22 plus 13.5, and then divide that by 2. Yeah, 17. I'm sorry, that's 75. So we'll go back. Misread. All right, and let's see what else we have. The angle that it gives us is 13.8 radians. And what else does it give us? Oh yeah, and then our final and initial is 22 and 13.5 for angular velocity. But it's right there, so I'm not going to write it down. All right, so how do we solve this problem? So we're going to use a permutation of the equation for displacement that we have, but since it's angular, it'll look a bit different. I'll get a different color. So the way the formula goes is it's a change in angle is equal to 1/2 of W initial plus W final times T, which is essentially just W average times C. So this is a W, that's my bad. Our angular velocity average times T. So our angular velocity average times T, so we already have this being 13.8 equaling to 17.75. And now we can find the time. Once we move those over and divide, our time is going to equal to 0.777. Now that we have that, we can set up a different formula. So just looking through my notes here to make sure I have everything. All right, yeah, perfect. So knowing that we have our initial and final angular velocity, and now we have our time, we can set up this equation to find our acceleration. And it reads like this. We have our angular velocity final equaling to our angular velocity initial plus our alpha, which is our angular acceleration, times the time. Now we have all three of these variables figured out. So this means that this is the perfect equation to find alpha. So we'll substitute in right now. Our W final is 22. That's 13.5 plus alpha times, what is our time again? It was 0.777. You could round that up, but I'm just going to use that number. So now if we were to subtract 13.5 from 22, we'll get 8.5 equals to alpha times 0.777. And now if we divide, we'll get alpha equaling to 10.94. And that is measured in radians per second squared. And which answer aligns with that? That is A. So our answer for question number 4 is A. All right, that makes perfect sense. This is very similar to our just one-dimensional kinematics, except this is taken with the lens of just being angular. So far, like its general premise is almost exactly the same, just with different variables. So I'll clear one more time, and we'll pick one more problem. We'll do we'll do number 6. I like number 6. All right, it's a short answer, so hopefully we're right here. All right, so got this purple marker. All right, so it reads like this. A 1.25 kilogram ball begins rolling from rest with a constant angular acceleration down a hill. If it makes if it takes 3.6 seconds for it to make it to the first complete revolution, how many will it take for the next revolution to be completed? All right, so a couple things. We already have our mass, which is 1.25 kg. And we already have the time it takes to fall down the hill, which is 3.6 seconds. What we want to find out first is we know that we have a constant angular velocity, but we have to figure out what that is. So the way that we do that is we set it up to be, hold on, I'm going to do this really quickly. I want to give us more room to write. So I'm simply going to white out the question below. It'll take us a quick little second. Just be patient with me so that we can have more room to just knock this question out. Kind of therapeutic, just whiting out the screen. All right, so now that we have a little bit more space, I might cut that out. If I don't, I sincerely apologize. Now that I have more space, we can set it up like this. So there is an equation that we got to know. It's our angular acceleration, or alpha, is equal to 2 pi over 1/2 of time squared. So we know what our time is. I'm going to make this smaller. So that equals to 2 pi over our time being 3.6. So what's 1/2 of 3.6? I don't know for exactly, but I'm just going to do 1/2 of 3.6 squared. And I'm just going to toss that in the calculator, see what I get. Okay, it is 0.9696. And that is our angular velocity. I'm sorry, angular acceleration. So now that we have our angular acceleration, we can find the time it takes to, like after our first 3.6, to find our complete revolution. So now that we have this new acceleration, we can find the time that it takes to revolve once more. So how would we set that up? So the way that we would handle that is we would take an equation that helps us with first knowing what our original value for time is with our initial angle and our secondary angle. So I will set it up like so. Angle is equal to angle initial plus velocity initial plus 1/2 of alpha t squared. Now that we have that set up, we can do a few things. If we plug in, we know that this goes to 0, and so does this, because it starts going from rest with a constant angular acceleration. Those go to 0, and now that we're left with is just this right here. And we're going to move that up in a different color. So we have our angle is equal to 1/2 of alpha, which is 0.9696 times or times squared. And our original angle was what? Okay, so now we just manipulate the equation like so. So we'll get our time isolated, and it'll end up being the radical of 26.1791. And now our final t will equal to 5.116. Okay, so now that we have that, our final time being 5.116, let me get my eraser out. That's fine, actually. Still just ignore all of this right now, because that's a different question. So now that we have our time equaling to this, and we know our original time for it to take was 3.60 seconds, all we have to do now is subtract this time by our original time, and we'll have an answer. So 5.116 minus 3.6, toss that in the calculator. And we get 1.516 seconds. And that's my answer. 1.516 seconds. And that's our answer for number 6. I believe I've done 3 questions. Now for chapter 9. So now I can move into chapter 10 because that'll take a little bit longer to do. All right, hopefully you can see this just fine. Let me make sure that I'm recording. Okay, I am recording. I was so terrified for a second that I just did not record my video. All right, so with my notes here, let's tackle a question from chapter 10, or a couple of them actually. All right, let's just get started. Let's start with question 1. All right, so a 1.1 kilogram wrench is acting on a nut, trying to turn it. The length of the wrench lies directly east to the nut, and the force is 150 newtons acts on the wrench in a position 15 centimeters from the center of the nut, 30-degree direction northeast. What is the magnitude of the torque of the center of the nut? So this one isn't that bad. We just have to first draw something out. So let me get my annotation tool, and we're going to draw our nut and our wrench. All right, so imagine this is our wrench. It is 15 centimeters in length. And then our nut is right here. Pretend this is our nut, right? That we're acting on. There happens to be a force acting upon the wrench in this direction. And it has an angle of, of 30 degrees, right? Because the wrench is left of it, east of it, I mean, and it goes 30 degrees northeast. All right, so what is the magnitude of the torque? All right, so torque can be measured, can equal our radius times force times sine of the angle. So we already have our values kind of given to us. We know that the R is going to be 15, our angle is 30, and our force right here is equal to 150 newtons. So if we plug everything in, Oh, wait. One thing, this is in centimeters. This needs to be in meters. So 15 centimeters divided by 100 is equal to 0.15 meters. So we'll plug that in. T is equal to 0.15 times 150 times sine of 30. So that would equal 0.15 times sine 30 is 1/2, I believe. So 150 divided by 2 is 75. And then that times 0.15. T, our torque, is going to equal to 11.25 newtons times meters. And that is our answer A. And that is the answer to our problem. Our torque is going to be 11.3 newtons times meters. All right, next up. I had difficulty with this question. I'm going to skip number 2. I do not like that question. All right, let's tackle, yeah, I suppose 3 is not that bad. So we have our r vector and our force vector. And we essentially, well, your question, what is the torque from about the origin of a particle located at r equals 3m in the I direction, 4j and 4 in the j direction, and -2 in the k direction. If a force F 5 in the I direction, -2 in the j, and +3 in the k acts on the particle. So the way we set that up is we have to do an ugly mathematic process. So essentially we'll set it up like this. It's going to be an array. So I'm going to get a different color. Let's use orange. Might be a bad idea. We'll see. All right, so our R will equal 3, 4, and -2. And our F will equal 5, -2, 3, all in here. And if we do the complex motion for it, essentially what's going to happen is we're going to have our I times 4 times 3 minus 2, -2 times -2 minus j times 3 times 3 minus 5 times -2 plus your k times 3k minus 2 times, whoa, hold on, 3k minus 2 minus 5 times 4. Now let me put that onto the calculator. For our I, we're going to have color 8 in the I direction. And then for J, we are going to have minus 19 the J direction. And then, okay, minus 23 in the K. And, oh, wait, whoa. Whoopsie. Quick little math there. Minus 26 in the K. And let's see if any of our answers match up with that. And answer B does. So our answer here is B. All right, we'll get another question. Okay, guess we'll do 4. All right. So a torque of 12 newtons times meters is applied to a solid, a uniform disk of a radius 0.50 meters, causing a disk to accelerate at 5.7 radians per second squared. What is the mass of the disk? Okay, so this one's asking for the mass. And it gives you a torque, it gives you your radius, and it gives you your angular acceleration. So what do we know? We have our torque, which is equal to 12. We have our radius, which is 0.5. And then we have our angular acceleration, which is 5.7. How do we get started with this? So first thing we should notice is that, let me get a different color. Torque is equal to our impulse times our angular acceleration. And again, it's asking for mass, but once we get understand what our impulse essentially means, we can find our mass. So essentially, impulse in this situation, like the way you describe impulse, is our mass times our radius squared. And then we still have our angular acceleration here. Now that we have that set up, we can isolate mass. So if we move everything over, it would be T. Oh, so we forgot to put a half here. 1/2 of our mass radius squared. So it would be 2T divided by R squared and then divided by alpha. Now we can sort of substitute in. So we get one more color. So it's 2 times 12, because we know that over here, divided by R squared, which is 0.5, and 0.5 squared is 0.25. But we'll write that in a sec, times 5.7, because that is our alpha. And what does this equal once we put it all together? It comes up to about 16.84 kilograms times meters squared. Oh, wait, no, just times kilograms. All right, so 16.84 kilograms. Which one of our answers has that? Let me clear this out with an eraser. Okay, it's gonna round apparently. So our closest answer here is 17, because 16.84 rounds up. It doesn't say to round in the question, so that kind of bothers me because there are decimals, but I'm gonna go with answer 17, which is, whoops, which is A. All right, next question. We'll do 5. All right. So a uniform disk has a mass of 3.7 kilograms and a radius of 0.4 meters. The disk is mounted on a frictionless bearing and is used as a turntable. The turntable is initially rotating at 30 rotations per minute. A thin-walled hollow cylinder has the same mass and radius as the disk. It is released from rest just above the turntable on the same vertical axis. The hollow cylinder slips on the turntable for 0.2 seconds until it acquires the same final angular velocity as the turntable. What is the final angular momentum of the system? So we are looking for not just angular momentum, but the final one. So how are we going to set that up? So we know this is a momentum question as well as an impulse question. So how do we set this up? Essentially, we know that the second cylinder lands on the disk and it continues going until it is the same as the initial disk moving speed. So what we can do is set it up like this. We will have our impulse initial times our, our angular velocity initial is equal to the added impulse initial, the first one and the second one, times our angular velocity final. So now we're looking for our final angular momentum of the system. And the way we do that is by isolating this variable. So we will get our angular momentum final is equal to our impulse plus our angular momentum initial, times over the two impulses. Now that we got that set up, we have to now remember what impulse means. Impulse, for the uninitiated, hold on, is 1/2 of your mass times your radius squared. Now we'll apply that here. So it would be 1/2 of mass 1 r squared times your angular momentum initial over one half of m1 plus m2 wait a minute. Oh, they have the same mass. So it would just be m1 and m1, just because they're both the same mass. It's the same variable, so it doesn't matter. R squared. Now here you can do a little bit of dividing. You can square these out and essentially have it to be oh, nope, I made a mistake. Let me get an eraser. I knew something wasn't right. I was trying to find it. So this would be 1/2 inside because this one doesn't have the same impulse. Okay, so now that we resume this, we can simplify and remove terms. So if we add these two together, we're going to get the same thing on top, m1 r squared over, and you add these together, you get 3/2 m1 r squared. And now you can cancel out this, and you can try and cancel out this, and you'll be left with a 3 on the bottom, which will equal your angular momentum initial over 3 is what's going to be your angular velocity final, or angular momentum, I mean. And now if you just take whatever your initial one was, in this case, it was 30 times your alpha, which is, hold up, let me find out where this variable is. Oops, wrote that down wrong. So 3.24 over 3 now will equal 1.08 in kg times meters per squared per second. And 1.08 is closest to 1.9. So our answer here would be E. Oh, whoops, no, whoops. I did a miscalculation. 1.1, there we go. So our answer here would be C. All right, let's quickly move on to the next question. Okay, this one will be fun. So in the figure, rotor gyroscope with the uniform disk has a radius of 13.8 centimeters and a moment of inertia about its axis of 4 times 10 to negative 3 kilograms per meter squared. And the length of the rotor shaft is 6.9 centimeters, and the ball pivot of P is frictionless. At a given instant, the rotor shaft is horizontal, and the rotor is rotating with an angular velocity of 90 radians per second as OP, which is shown. Yeah, it's looking at the length, which is this. This is OP, which is axis. The rotor is viewed from QA's axis, and the precessional linear velocity of O, including the direction seen from Q, is closest to. All right, okay, so we can set this up like this. So we have our I, which is equal to inertia, which is 4 times 10 to negative 3. And then what else what are we given here? The length of the rotor shaft is 6.9 centimeters. So we want to turn that into meters. So it would be 0.069 meters. And then our 90 radians is an angular velocity of 90. So how do we set this up? We remember what inertia means, which is mass times our radius squared over R2, which now if we're looking for mass, is going to essentially translate to mass is equal to 2 times inertia over R squared, which is essentially going to be 2 times 4 times 10 to the negative 3 over 0.138 squared. Oh, and yeah, we're given our radius as 13.8. This is centimeters, you divide by 100, so 0.138. All right, so now if we fully divide that, our mass is going to equal 0.42 kilograms, and we are not done. Now that we have that, we have to calculate for our length. So our length I'm sorry, not our length, our linear velocity. So our linear velocity is going to equal to our mass times gravity times, let's call this Li, times L over our inertia times our angular velocity. Now, if we stack that all up together, it's going to be, I'm not going to write all that down. I'm just going to calculate this really quickly. (0.789). Now that we have that, we multiply for velocity. We have our original 6.9 times 10 to the negative 2, which is the same as what we were given there, times our 0.789. And that'll essentially sum up to being 0.054 meters per second. And this is positive, so it is rightward. Our answer is D. whoops, that is an ugly D. All right, and that's number 6. I'll scroll down one more. We have one more problem we need to do. Let's pick something deeper down. Let's do number 13. All right, so a potter's wheel with rotational inertia of 46 equals 46, spinning freely at 40 rotations per minute. The potter drops lump of clay onto the wheel where it sticks for a distance of 1.2 meters from the rotational axis, and its subsequent angular speed of the wheel of the clay is 32 rotations per minute. What is the mass of the clay? All right, that doesn't seem so bad. So firstly, we want to take this 40, multiply it times 2 pi over our time times 2, so by 30. Okay, so by 60. Oh, because it's a minute. And that'll give us 4.18 rad per second. Now that we have that, we can sort of get started. Our variable here would be 1.2. And that is our distance. And then we know that there's a 32 RPM, so that would be our second one. 32, which will be given the same treatment, 2 pi over 60, which will equal 3.35 rads per second. I'm not going to write it. So now we set this up, since this is kind of a conservation of momentum problem. We do our inertia times our angular velocity, equaling to our inertia 2 times our angular velocity 2. The inertia will be conserved. So let's just start plugging things in. We have 46. I'm gonna use a different color. It's too much pink. 46 times 4.18 is equal to, in parentheses, our 46 plus m times 1.2 squared outside 3.35. That essentially equals to, I'm going to go on this side now, 192.28, which equals to, let me do the math, 154.1 plus 4.82. Sorry, m. So now that we have our m, that'll equal to about 8 kilograms, which is C. All right. And that's all the problems we have for 9 and 10. So thank you so much for watching and have a good day.